Hello, my name is Colin, and I am in Group 13 with Jose, Joseph, and Ahmed. And today we will be demoing out sections of our project of the low-power variable optic with automatic distance correction. The main goal of this project is to provide a variable magnification on a rifle scope that has an attached rangefinder and will automatically change the reticle, so that way the user can automatically adjust their target depending on different distances calculated in with the bullet drop over a specific distance.
We used EasyEDA to design our PCB boards for the project. This is the first board that we designed. While most components worked, we had a few issues. The first was the USB to I2C component. When we designed the board, we used the surface mount component when what we really needed was a through-hole component. The next issue was our display connector. The display connector had pins only on the top, while we needed pins on the bottom of the connector to connect our display. This meant we had to redesign the board. After a quick redesign, we came up with this. We now have fixed the USB to I2C to use through-hole, and our connector has pins on the top and bottom. We also managed to get the board to be a little bit smaller, which was helpful. Also, we were able to include more input and output pins on the board, giving us more options if we needed.
This is a printed circuit board which includes all the electrical design of the USB to SPI interface, and the others such as the Atmega 328 PPU and the OLED display connection. The USB to SPI interface is mostly located on the bottom left. It is equipped with an SPI interface that enables USB connectivity for the smartphone app integration. This is the USB Type-C connector, and this is the microchip that converts the signals from the USB to SPI. The USB Type-C connector inputs the power and signals and communicates with the microchip MCP221I/SL. Then the microchip distributes the signals to the corresponding output pins located on the bottom and right side of the board, and also with the OLED transparent display connection located on the left side of the board. The following is a one-line diagram that demonstrates the distribution of power from the power source to the different components, which are all on the PCB except for the SR button and the rangefinder. We're using 3 voltage regulators to power all of our components from the 9.6 volt battery power source. Our design has 3 voltage levels to choose from: 3.3, 5, and 12.77 volts. This allows to satisfy the voltage requirements for all the components with a simple design of just using one battery. It works great for our lightweight and slim goal, as it only weighs 45 grams in comparison to 3 batteries weighing over 100 grams.
Hi, this is going to be a quick overview of the software used to program the microcontroller. First, we're going to start off with a quick setup of the display, the button, and then the rangefinder. Following that, we're going to go into a loop where we would poll until the button has changed its state. Once the button has changed its state, we will go into the read range function, which will handle most of our logic. We'll wait to send the turn on command here, retrieve the data here, and send that turn off command here. Once we have received that data, we would go ahead and convert that to a float, to which we would start doing some calculations with it, such as calculating the fall off and the angle. And then from there, we can use those parameters to display the compensation pixel.
This works as the main housing for the eyepiece of the ocular system. It's going to house 3 lenses. You have a focal lens on this end, which is what's going to set the eye relief for the user as well as display the final image on their eye, as well as a second eyepiece lens that's going to help to ensure that the system reaches a proper magnification. The variable magnification of the system is going to be achieved using this third lens, a biconcave lens that's going to be on a movable system on translation stage. For our demo, we're using a slider that achieves the 1 times magnification all the way up to the 6 times magnification. This section only serves as the front eyepiece. It's not the entire scope. It will be connected to a smaller housing, which is going to be a more narrow diameter. This is only going to be about 35 millimeters in diameter at its point. And it's going to house the image reversal assembly to ensure that the user is seeing a right side up image, as well as the objective lens, which is what is going to ensure that the user has a solid field of view, as well as appropriate parallax for their distances. This slit that's on the bottom is where the OLED display is going to be able to fit into, and it rests at the focal distance of the objective lens, as well as double the focal distance of the image reversal assembly. So this acts as the reticle. The goal for this is that will be the image that is displayed on an object when the user is using the scope, so that way they seem to overlay so the user knows what target they're going to hit. These two pieces are going to be affixed together to create our compact system, which falls at just about 300 millimeters. So although about a foot long still seems a little large, in the overall scheme of what exists on the market, this is going to be relatively small. We're using a 5-lens system. One is currently inside working as the objective lens. The focal lens is going to be the largest at 40 millimeters. So that way the user is going to have a clear view, as well as something that fits the general size of their eye. The only lens that is not a biconcave is going to be the biconvex magnifying lens. And the other two serve the purpose of ensuring that the proper magnification is created, as well as with the image reversal lens, that the lens is going to be in the right orientation so the user has a proper image.
This is going to be the 3.3 voltage regulator testing. This is the printed circuit board. These are the connections made from the 9-volt battery. And these are the cables to the multimeter. We're going to be using a button to test. As you can see on the multimeter screen, it reads 3.3 volts, fluctuated a little, but this is a success for the 3.3 volt regulator. This is going to be the testing for the 5-volt regulator. This is connected from the 9.6 volt battery to the multimeter. As you can see on the multimeter screen, it reads 5 volts, so that shows a success for this connection, and the PCB is working great. This is going to be the testing for the 12.77 voltage regulator. As you can see, it's been connected from the 9.6 volt battery to the multimeter on the output end. The multimeter reads 13.00 voltage. This is shown as a success as it steps up from the 9.6 volt battery to the 13 volts on the reading.
Here is a basic demo of the OLED display. We start by drawing a grid of squares onto the display, clearing the display, and then drawing text onto the display to test everything. In this demo, we demonstrate the USB functionality of the board. We can send messages and receive messages. Here we are sending a hello and goodbye message.
This is an app demo for connection to our microcontroller. As you can tell, there are 3 buttons: one to connect to the device, one to send data, and one to request data. Currently, this is a work in progress, so doesn't work 100% of the time. But connecting to the device is simple as no connection available. This is by creating an MCP221 COM object and checking if that COM is open. If it is, we share that status, and if not, we just show that no connection is available. Sending data to the phone, as simple as typing data 1234, and then if we send that data over, we see sending data 1234. that will be sent through that same MCP to 1COM. And then requesting data works the same way. Simply just requests data, and from that is the object name. And that is our full project from top to finish. This is our startup sequence. When we're first connected to the power source, it runs through the check of the display. Shortly after, it starts to check of all the components, and then it reads a range right off the bat, and then displays that pixel, that composite. And then this is us pressing the button again. We see at certain points that there's no value. Following that, we see that we actually do get a range as soon as we press that button, and then we get a pixel right there. And then as well as you can see the rangefinder being changed according to a certain distances, and we can see that reflect onto the display itself.